Hello again, and welcome to my series of videos on high-frequency electronic design with Microwave Office. My name's Steve Moss. Today I'd like to talk a little bit about microwave hybrids, both types, that is 180 degree and 90 degree hybrids, and say a little bit about what they are, how they work, what their characteristics are, and finally how you design them. Now, what exactly is a hybrid? A hybrid is a 4-port device. It's passive, linear, and reciprocal. In any hybrid, we excite one of the ports, and 2 of the ports are outputs, and the 4th port is isolated. So for example, if I excite port 1 in this 180 degree hybrid, I'll get outputs at port 4 and port 3, and 2 will be isolated. If I excite 2, then the outputs are again 4 and 3, and 1 is isolated. But in a 180 degree hybrid, if I excite port 2, the phase difference between the signals at 4 and 3 is 180 degrees. And these lines that I've drawn here kind of indicated that 2 to 4 gives you the 180 degrees additional phase shift, and 2 to 3 gives you nothing additional. And by following those lines, you can see exactly what is happening if you excite other ports. For example, if I excite port 3, the outputs are 1 and 2, and they're in phase. There's no phase difference between them. Now here's a 90 degree hybrid. In a 90 degree hybrid, we have very much the same sort of behavior. That is, if I excite one port, I will get outputs at equal levels at 2 other ports. So for example, if I excite port 1, I'll get outputs at port 4 and port 3. The difference between this and the 180 degree hybrid, of course, is that now we get a 90 degree phase difference between the 2 ports. And it doesn't matter which port you excite. That is, if I excite port 3, I'll still get a 90 degree phase difference between the output ports. And so forth. You can see from each port here, if I excite 2, same story. If I excite 4, same story. And of course, as before, there's 2 outputs and 1 is isolated. Now, as it happens, these are the only 2 types of hybrids that can exist. That is 180 degree and 90 degree hybrids. Nothing else is possible. So don't waste your time trying to come up with a 45 degree hybrid or something like that. It can't be done, at least not as a passive, reciprocal, lossless device. Now, how do I know that? It comes from the mathematical properties of the scattering matrix. It shows very clearly that these are the only things possible. So that's mathematically proven. And I'm quite confident in saying that quite so absolutely. Now, how do we come up with a 180 degree hybrid? Well, here's one way you can do it using a transformer. The port numberings here are the same as in the previous figure. So for example, port 1 and 2 are mutually isolated. Ports 3 and 4 are mutually isolated. And for example, if I excite port 4, ports 1 and 2 have the output. Now, these aren't terribly useful for microwave purposes, but I thought I'd include it mainly for historical reasons. Transformer hybrids like this were used throughout the telephone industry back in the early days of telephony, and they were useful for separating the user's voice from what he was listening to coming down the line. You didn't want to talk into your own ear when you were trying to talk to someone else. So you would connect the microphone and the earpiece to mutually isolated ports and the line to one of the output ports. And the 4th port could just be terminated. I understand these were actually unbalanced a little bit, so you could hear a little bit of your own voice while you were talking, but not too much. So that's one way you can come up with a hybrid. I suppose you could still do this at relatively low frequencies up through the RF region, and it wouldn't surprise me if it's done fairly often. Here's a very common type of 180 degree hybrid called a rat race hybrid. It's a microstrip structure, usually, and it consists of 4 transmission lines. That's really it. A quarter wavelength here, another quarter, and then a 3/4 wavelength line. Again, I've numbered these ports like I did in the previous 2 cases. So 1 and 2 are mutually isolated and 3 or 4 are mutually isolated. Now you can see, for example, it should be pretty clear that if I excite port 1, the outputs are going to be 4 and 3 because this 3/4 wavelength line, it's 180 degrees longer than this line, so this point has to be a virtual ground. So looking into this piece of transmission line, you see an open circuit because it's just a shorted quarter wave stub. And it's the same story here. It's 3/4 of a wavelength instead of 1/4, but looking into this point, you're going to see a open circuit. Now, the same thing pretty much holds if you were to excite port 2. That is, the output would be divided between 3 and 4. And again, because of the 3/4 wavelength here, this is going to be virtual ground here at port 1. So again, the line from 1 to 3 becomes a shorted stub. So you're looking into an open circuit, and the same way for 1 to 4. And you can keep using that reasoning to show that the ports are either outputs or isolated. Now, in the case where 2 is excited, it should be pretty clear also because of the extra half a wavelength here that ports 4 and 3 are 180 degrees out of phase. From the figure, you can also see what the characteristic impedance of the lines are. If the load is R at each port, and fortunately it's equal at all the ports, the characteristic impedance of this ring is R square roots of 2. So for 50 ohms, you've got about 70, 71 ohms here. It's very realizable. It's not a problem at all in most cases. One nice thing about the rat race hybrid is its planar structure. We like to use rat race hybrids for mixers, for example, where a balun might be possible, but the planar baluns are a little harder to come by, and you don't want a non-planar balun if you can avoid it. Another disadvantage of this structure is that it's often too big at low frequencies and too small at high frequencies. At high frequencies, these lines can get so small that the junction parasitics dominate, and then it doesn't work very well. On the other hand, at low frequencies, very often it's possible to take these lines and meander them a bit to reduce the amount of layout space that it takes. And there's nothing that says this hybrid has to be made in a circular structure like this. You can make it square, you can make it, as I said, meandered, or all kinds of things, whatever your heart desires, consistent with all the usual considerations of not having coupling between lines and all of that. Now let's go to the computer and design a rat race hybrid. I'm going to use the component synthesis tool, as I did once before, not because the rat race hybrid is so difficult to design, but it just speeds up the process quite a bit. So I'll select a rat race hybrid, and let's make it 5 gigahertz center frequency for a change. You can't select the fractional bandwidth. There is no degree of freedom for doing that. And of course, we'll keep 50 ohm port impedances. Now for microwave, I think I'll pick Illumina, which is 9.8 dielectric constant, and you can see the boxes have been filled up here. So let me synthesize it and then send it to Microwave Office, and here we have it. And let me clean up the graph a little bit so you can see it. So here we have our power divisions along here. They're all about the same. It's 3.3 dB in this case, maybe 3.1 at the center of the band. And the isolations look pretty good. From 4.5 to 5.5 gigahertz, they're well below minus 20 dB in terms of return loss and isolation. This is over 4.5 to 5 gigahertz. That's 1 gigahertz centered to 5 gigahertz, so we're looking at 20% bandwidth. And this is about what you see with practical rat race hybrids. Now, if we look at the line dimensions, which I've set up as variables here, the width of the ring is 268 microns, and the length is about 5 millimeters for the short quarter wavelength line segments, and about 18 millimeters for the longer segments. These are eminently practical values. So for something like 5 gigahertz, 10 gigahertz in there, and even to higher frequencies, these are very practical hybrids to use. And 20% bandwidth is nothing to sneeze at. That's fine for all kinds of circuits. Finally, as a preview of coming attractions, I thought I would show you this mixer using a rat race hybrid. This mixer operated at about 30 gigahertz. It was designed for the ACTS communication satellite, which unfortunately never was built. You can see the RF input and the LO input at the top and left side, and you can see the IF filter toward the bottom, and of course the rat race is obvious. The diodes, of course, are beam lead and they're too small to see. This mixer was built on an a fused silica substrate, dielectric constant about 3.8. And that made the size large enough to be practical for what at the time was a pretty high frequency. So here it is. We'll talk about rat race mixers a little bit more when we reach the subject of mixers. Well, what about 90-degree hybrids? Here's one kind which has been around forever, and it's used pretty extensively. This is called a branch line hybrid. You see the characteristic impedances. This line is R, these lines are R over the square root of 2, and they're all quarter wave length long, of course. Now you can see if, for example, port 1 is excited, the outputs will be ports 2 and 3, and there will be an extra 90 degrees of delay for the signal getting to port 3. So port 3 will be delayed 90 degrees relative to port 2. And you can use the same kind of logic when any other port is excited. Frankly, these are not great hybrids. There are other kinds that work a lot better. Most notably the so-called Lang or Lange hybrid. I'm sorry, I'm not real clear on how that name is pronounced, but those have much better bandwidth and much better characteristics. They're a little harder to make though, and for narrow bandwidths, these tend to be used a lot more than you might think. Again, let's go to Microwave Office and design ourselves a branch line hybrid. Again, I will use the component synthesis wizard, not because the circuit is difficult to design, but just to save some time and hassle. So we'll select a branch line hybrid. Let's make the center frequency 5 gigahertz. Again, I like 5 gigahertz. Again, there's no degree of freedom to adjust the bandwidth, so that's what it is. Go to microstrip setup, and just for change, I think I will make this on a Duroid substrate, 5880 in this case. I'll put it in mils too. So let's send it to Microwave Office, and here is our design. There is a hybrid, and let's take a look at the performance. And get this legend out of the way. And you can see that we don't have anything like that 20% bandwidth of the rat race hybrid. 20 dB, it's about 4.8 to 5.3 gigahertz, so it's about a 10% bandwidth there, nothing terribly spectacular. You can also see there are different losses to the different ports. So you don't have anything like the balance that the rat race hybrid had. But on the other hand, if you need a 90-degree hybrid, you'll need something like this, or maybe one of the other types. Now here's our circuit. I'm going to try doing a layout of this just for fun. Bingo, there it is. And so this is our port 1. If that's our input port, this is one output port, and this is another output port. So you can see also that even at 5 gigahertz, this is starting to get a little small, and it's on Duroid substrate, which is like a 2.3 dielectric constant. It's not a high dielectric constant substrate. So one of the problems we run into with these is, especially with these wide lines, you tend to have impractical dimensions at a not terribly high frequency. Now there's one more point I want to make before we completely leave the subject of branch line hybrids. And that is that the branch line hybrid can be realized in multi-sections in order to get more bandwidth at the cost of a little bit more real estate on the circuit board, or the IC as the case may be. So let's try making another one here. You notice you can pick the number of sections up to 3 sections. We'll make it 5 gigahertz again, center frequency. And of course 50 ohms. And let's go on to the microstrip setup, continue to use our Duride 5880, and I'll put it in mils as well. Okay, so to microwave office, and there it is. Let's run the analysis. And here is our hybrid, 1, 2, 3 sections. And here is the performance. You can see it's not spectacular. We've got a little better than 15 dB return loss across about a, well, what is the bandwidth? Let's say from about 4, a little over 4 to almost 7 gigahertz. So it's maybe 6.7 to 4, maybe 2.7 gigahertz. 2.6 gigahertz over 5 gigahertz center frequency, that's a little better than 50% bandwidth, which is nothing to sneeze at for sure. Now, this isn't as nice as you might imagine. We've got 3.6 and 2.7 dB, that's almost 0.9 dB imbalance on it, which is tolerable for many things, but not for everything, of course. So this isn't perfect. Another thing that happens, I don't think you'll see it here immediately. I approximated some of the lengths of the branches, the cross branches here, so that it would lay out properly. That is, you wouldn't have a problem with one line being longer than the other. You can certainly see there'd be a problem if that happened. So you would have to meander one of the lines, but the difference wouldn't be that great, so it would be hard to meander. So this is probably not a perfect design. What you can do is open your faithful tuner and start tuning. Although with this many variables, it might be better simply to run the optimizer, but we'll play with the tuner a little bit. I seem to find that changing the impedances of the shunt line seems to do a lot of good. You can see it has a strong effect on the balance at some cost to the bandwidth. And let's see, width of shunt 1, do this, has much the same kind of effect, and so forth. So you can diddle this to your heart's content and maybe get the thing to work a little better. See, already I've got a below 20 dB return loss with about the same imbalance. So that's what you can do to make a multi-section branch line hybrid. It's not a terribly satisfying design, but it's very simple, it's very straightforward, and it will be useful for many different kinds of circuits. I hope that's a useful introduction to microwave hybrids. There's still one I need to talk about, which I decided I will leave until I describe directional couplers, and that of course is the Lange or Lang hybrid. That hybrid is actually not very different from a directional coupler, so in order to understand it, you'll have to understand directional couplers, so we will leave it till then.